to practice safety and stuff.
Isn't that just dumb?
It is. Yeah,
Are we all really going to go out?
making sure we know what we
No,
do.
we're not.
If there is a fire, are we all really going to go out in an orderly fashion? Or am I
If there's a fire,
You want the honest answer?
if there's a fire, we all can leave the building. It's a big fire then.
All right. There's no fire. It's getting kind of warm, but it's 3 a.m. I'm sure the sprinklers will take care of it. Can't be bothered with this. All right. We got it all right. So we were making our way through the conjugated pi systems kind of part of the class there, and really it's just an intro to get into the aromatics. There's not too much to say about conjugated systems, aside from just kind of starting to pay attention to the idea of the kinetic and the thermodynamic products, although in reality this stuff doesn't really show up again in this class, but it's kind of a good intro reminder of resonance structures and being able to draw those, and really starting to pay attention to the allylic positions in molecules, right? So the carbon that's next door to a pi bond there is a good place to make a carbocation, right? Or even a carbanion, or even a radical, right? Any of these kind of intermediates that that need to be stabilized, right, through resonance. And so resonance is going to be our explanation that we have for the mechanisms that we're going to end up going through in this next part here. And basically the next part is all about how to deal with benzene rings, I should say, and their substituents. Right? And it's all based off of resonance. Okay, that's really all it comes down to. Now the other end of it, what we're going to have to learn, or what we're going to have to start to pay attention to is, I guess we could call it inductive effects again, which is basically, remember how we can just like push and pull electrons through bonds, right? So back when we first went through the acid-base chapter of OChem, we talked about how inclusion of the electronegative atoms, right, on the molecule pulls the electron density towards the electronegative atoms, and it could make things like carboxylic acids more acidic, it could make alcohols more acidic, all this kind of stuff, right? And so the same idea is going to be at play in aromatic systems. We're going to start to have to look at what is on a ring and how that affects the electron density on the ring. And whether things are withdrawing electrons or pushing electrons or donating electrons or whatever it might be, is going to have an influence on where things get added to the ring itself, okay? So we're going to have to start to think a little bit more about how we disperse electron density, right? And resonance and inductive effects are going to be kind of our two big topics, I guess, or ideas that we're going to call back again and again, right? So that's where we're going to go with that stuff. All right, but before we get to that, we're going to have to actually define, oh, there it is. We're going to actually have to define what an aromatic system is, right? All right, okay, wrong size. Let's try this once more. There, cool. So, the definition of an aromatic system is based off of kind of 3 check marks that we have to go through, okay? And so, just for, I guess, maybe a little bit of a historic context, it used to be thought that aromatic compounds are the things that give rise to aromas, right? So that's where the name comes from. It doesn't actually necessarily mean that, although a lot of aromatic compounds do have strong smells, but they're usually like garbage smells, right? So we don't, there's no one like takes a whiff of benzene and, you know, goes, ah, right? Soothing, right? You know, a little behind the ears, right? Okay, they just have these solvent type smells, right? In reality, and this is kind of what we're doing in lab, well, some of us are doing in lab. Our carbonyl groups tend to give rise to more of these kind of common sense right, that we run into. But aromatic systems are certainly part of a lot of common smells that we run into also, but it's not necessarily due to the aromatic system, right? So it's kind of just a name from antiquity is all it is. So for our purposes, aromatic is just really going to mean, hey, it checks these 3 boxes, right? If a compound, right, if a molecule, I should say, if a molecule checks these 3 boxes, then it is considered aromatic. If it is aromatic, then it behaves and reacts in a specific way, right? That's the thing to pay attention to, right? So that's why it's sometimes introduced as a functional group, and that's true, right? These do have unique properties. They do behave in a unique way. They have different acidities and basicities and intermolecular interactions. All these things are different when you see an aromatic group, okay? So the reason why I guess this is on my mind is because I'm finishing writing a paper and they're talking about these aromatic systems as functional groups, and I just got me, I don't know, it's, like I said, I almost forgot about class. I mean, it's going to happen one time this year, like it just will, because like in the afternoons I'm just going, right? I'm chugging along. I had lunch and, you know, woke up from that after my calorie coma there, and I'm just, you know, going through getting the work done. And I, thank you, Annie. That's the appropriate response. Right? So anyway, I just have this on my mind, and I guess because you guys are stuck in your seats, you have to listen to my rant. So if I'm ever not here, just I'm probably in my office, and not that I don't think you're like, yeah, I really want to learn, Dr. A. So don't take it personally if I sound like this forget, okay? But I'm setting an alarm on my phone. All right, forget that. So, anyway, so all that aside, right? So let's talk real quick about benzene, and to be fair, most of the time we're going to be just dealing with benzene in this class, right? And I'll give a couple examples of some other aromatic systems that are extremely important that you guys will run into over and over and over again, as long as you're kind of in the realm of chemistry. But for the most part, we're just going to be dealing with benzene in here, right? All right, what's our checklist here? All right, so what is the criteria that we need to meet? First one's kind of easy. It must be a cyclic compound. CYC, cyclic. Let's try this one more time. CYC, cyclic. There it is. Okay. Let's see. Let's say this here, containing a number of electrons. Okay. All right. And I'm going to come back and I'm going to define exactly what I mean by a number there. I'm going to tell you guys that number, and then you guys are going to immediately forget what that number is, and you're going to not understand what the number is, and you guys are going to go, Dr. H, what's that number mean? It's just there, right? It's just a number, right? And you go, oh, okay, all right. And then, I don't know why, this tends to be one of these tricky parts, okay? It's just a number, just to check one of these boxes. If number true, then meet criteria. That's all it means, got it? Okay? You're still going to ask a question. All right. Each atom in the ring, let's say, must have a usable p orbital. All right. Okay. So you'll notice that as with any good definition, I'm making this extremely vague. That way I can't ever be wrong, right? But you guys can, because you don't know my arbitrary definitions of things, right? That's learning, right? Yeah. No, right? So we'll come back and talk about what a usable p orbital exactly means, right? So that part is going to relate to what we were talking about with these conjugated systems, okay? And the MO theory and that kind of stuff that we talked about there, right? Basically, number two could be part of the definition of saying we could make hamburger buns, right? We have to make sure that these p orbitals can talk with each other. That's all it is, right? But 2 and 3 often go together. And so sometimes some books say there's only 2 rules to it, but 2's not marketable, 3 is, right? So we'll say 3 rules, okay? The p orbitals, okay, must be next door. Okay? It must be able to overlap, might be another way. Okay? Now, really another way of saying point number 3 there would be that we're able to draw resonance structures with all the stuff in the way. Okay? That's kind of what it says. Or what it's trying to say. Okay? Now there's something that's being defined by these 3 parts aside from the definition of aromaticity. The other kind of criteria that has to be met for number 3 to be true is that we must be in a planar system. Okay? So this must be a completely planar ring. Alright? Now the reason why I don't put that as a separate point is because if 1, 2, and 3 are met, this thing's almost always going to be aromatic. Okay? And it's going to force the geometry to be planar. Okay? And we'll give an example of that very, very soon here, right? But the point being, you know, we're drawing stuff on 2-dimensional paper. Like, when is your stuff not going to look flat? Right? You guys get what I'm saying with this, right? And if everything has a pi bond or something like this, then the hybridization is all going to look like sp2, which for our purposes all means that we expect it to be flat also. Got it? Here's what I mean with this. Okay? And here's the example that they put in the book. So we have a ring. Okay, we've got a bunch of pi bonds in there. If I asked you guys to guess what the geometry is, you guys would look at all the carbons in there. Everything is sp2 hybridized. You guys would say that, oh, everything's sp2 hybridized, therefore it has to be planar. It's not. Right? This thing is actually not planar. How would you guys know that? I told you it was in the book. And you guys were, I told you it's in the book. But you guys get the point, joking aside, right? We wouldn't really know. Right? I didn't know. Right? The only reason I remember it is because it's thank you. Okay, I read the book. Right? But this is why I don't really include that in there, right? You know, this is one of those gotcha type things, right? I'm not going to do that, right? I'm not going to make sure that everything checks the boxes from 1 through 3, and I'm like, those fools didn't know that it's not planar, right? So that's why I kind of leave that off. But that is a definition of it, right? This has to be a flat molecule also. Now, if it wasn't flat, right? If it wasn't flat, then each of the p orbitals couldn't talk to each other either, okay? Because these p orbitals have to be aligned in a specific way, right? So it's kind of included already in the definition there. Does that make sense though, right? You know, it's I know it's kind of a little bit nebulous at the moment still here, right? You know, but it has to be planar for the stuff to be met anyway, right? And that just comes down to how the hamburger buns are made, right? These p orbitals have to be next door to each other. They have to be oriented in the same direction, right? And they have to be perpendicular to each other, right? If they're off, right? If they're off axis or anything like that, the overlap doesn't happen. Okay. Cool. All right. So now let's talk about the number here. Okay. So this number, H-U-C-K, okay? I always forget how to spell the guy's name. H-U-C-K-E-L. Huckle number. That's what it really comes down to, okay? So when we read through the book and you see this online and everywhere, they say, okay, for a system to be aromatic, it has to have a Huckle number of electrons, okay? So So Huckle's the guy that came up with this. He also discovered the berries. That's where they get their name from. That's complete crap. I'm making that up, but it sounds impressive, doesn't it, right? I'm joking, right? But anyway, so if we have a Huckle number of electrons, okay, that has to be the number that is met, okay? That has to be the number that's meant for something to be aromatic. All right, so how do we figure out what a Huckle number of electrons are? Well, a Huckle number falls into the equation of 4n plus 2, okay? If we have 4n plus 2 electrons in a system that is a ring where the p orbitals are usable and they can talk with each other because they're next door, then we have an aromatic system. Got it? That's what I'm just saying, right? That's steps one, checklist 1, 2, and 3, right? So what's your question?
What's N?
N is anything you want it to be, okay? From 0 up to infinity. Got it? Now, of course, you can't have an infinite number of electrons, but you guys get the point? It's an integer value. And this is where you guys are going to ask the question, what does N have to do with the compound? Nothing. Okay? It's just a counting factor. The N doesn't tell us how many electrons there are. The N plugs into the equation to tell us how many electrons there needs to be. Got it? Does the N represent anything physical in the universe? No. Okay? But the point is this. If N equals 1, okay, then my Huckle number is 6. That means I have to have, right, 6 electrons in a ring in the p orbitals that can talk to each other, that is flat, and if it has 6 in those conditions, then it will be an aromatic system. Does that make sense? If N equals 2, right, then my Huckle number is 10. That means if I have a ring and they can talk to each other and it's flat and they're next door and I have 10 electrons, then it is aromatic. Got it? Yes?
If like all 3 things were met but the Huckle number isn't met, then it's no longer.
It's not aromatic. It's anti-aromatic is what we would call it.
And if
Or non-aromatic.
and if the Huckle number is met, but like one of the 3.
It's not aromatic, right? It's all or nothing, right?
Okay, all or nothing.
Much like every exam in this class, there is no partial credit. Okay? You guys add a carbon. Okay? No, mid school. Okay, right? So it has to be, so the N doesn't represent anything, it's just a counting value to make the equation, right? To make the equation work so that we can calculate how many electrons we need. Got it? So it's 6, it's 10, right? If N equals 3, then it'd be 14, right? Then 18, then 22, then blah, 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 blah. Got it? It's just increments of 4. Okay? Yes? Yes. All right. So, here we are. Let's take a look at a very odd compound. Okay. 1, be a cyclic compound containing a Huckle number of electrons. Okay. How many pi bonds does benzene have? 3. How many electrons are in each of those bonds? 2. 3 times 2 is 6. Is 6 a Huckle number? Yes. 6 is a Huckle number that fits the equation for n plus 2 when n equal 1. Got it? Does n represent anything for benzene? No. The 6 is the important part. Got it? Therefore, it is cyclical and fits a Huckle number of electrons. Each atom on the ring must have a usable p orbital. Okay, so a usable p orbital is a p orbital that is part of a pi bond. A vacant p orbital, or in some cases, a lone pair. I just described every single darn thing that exists, right? You guys, right? The only exception is if you have an sp3 hybridized atom that can't violate the octet rule, okay? Do you guys catch what I'm saying though? To do this, it doesn't have to be just pi bonds. We can also deal with lone pairs and vacant, open spots, okay? Open orbitals. Good? Well, we don't have any open orbitals or vacant spots. Every atom is sp2 hybridized in benzene, right? And part 3, those p orbitals are next door to each other. AKA, we can start to draw resonance. Can you guys draw resonance structures from benzene there? Okay? Therefore, benzene meets all 3 criteria. Therefore, it has to be aromatic, and then it falls under a certain classification of reactivity. Got it? That's all it is. So, your question is, okay, why is this going to take us 2 chapters? Right? If only life was that easy, huh? All it is, right? I told you these are the 3 rules, we can't violate them, right? So if I take, now you guys don't copy this down, right? If I take benzene, and you'll see why not to copy it down, don't worry. Crappy drawings incoming, okay? If I take benzene, and instead of representing it, right, with the line structures that we have, right, instead of representing the pi bonds with the line structure, if I back out and represent everything with my p orbitals, right? That means there's a p orbital here, right? There's a p orbital here, there's a p orbital here, there's a p orbital here. Okay, and remember, by the rules of MO theory and these rules that I haven't explained to you and that I won't explain to you because it takes way too much time and it's not really relevant, you'll just have to take my word for it, okay? There's a combination wherein all the p orbitals look like that, okay? All those p orbitals are next door to each other. If a p orbital is next door to each other, they can talk to each other. Got it? How many electrons live in that one hamburger bun that's made by this? 2. You guys got it? 2 electrons live delocalized around the entire 6 atoms of this benzene ring. Do you guys catch what I'm saying with this? 2 electrons are bouncing around all 6 of those carbon atoms in one of the hamburger buns. The book has really good pictures about this stuff, right? So, this is all I'm trying to pull for. You guys with me on this? Is this still a pi bonding combination? Is this electron density above and below the plane of the atoms? Yes. So we would say this is 1 pi bond, okay? Not a double bond in between 2 things necessarily, but a pi bonding combination, okay? As I take a step up in energy, okay? As I take a step up in energy, I add a node. And a node is a place where we switch the sign of our p orbitals. Right? The node will happen to fall diagonally across here. Okay? This happens to make a pi bonding combination also. How many electrons live in this weird looking hamburger bun? 2, okay? Still only 2 electrons can live in any orbital set, okay? So what does this mean? Pi bonding combination, right? Pi bonding combination. How many pi bonds do we have so far? 2, right? We take another step up in energy, and we draw a different node. This is what we get. Okay. Now you'll notice that orbitals, aka electron density, can't exist at a node. A node is where the function drops to 0, right? So you have 0 probability of anything existing there. Why can't electrons exist in the nucleus? Mathematically, it's a node, right? Electrons can't exist there. That's why they aren't there. Right? Have you guys ever thought about that? Why don't electrons just fall into the nucleus? Negatives attract positives, got it? Well, they just can't exist there. Oh, gross, right? Does that even make any sense? Thank you. That's the response I wanted. Well, whatever. The mysteries of the universe. Okay. So we still have a set of bonding combinations here. Okay. How many electrons can live in this set? 2. Okay. If we stepped up again, we would start to get into anti-bonding combinations. Okay. We would start to get into anti-bonding combinations. And electrons aren't populating the anti-bonding population, let's try this again with coherence. Electrons don't populate anti-bonding orbitals unless there's something unusual going on, right? So but that's, I'm simplifying that a little bit too much. But for our purposes here, we can just kind of stick with that statement for now. Yeah, what's up?
Why does the last one only have 4 electrons? And like, why is the node like?
I didn't, no. Each one of these has 2 electrons.
No, like 4 little orbitals.
Because the way the node exists here is that it falls along 2 of the carbon atoms.
Okay.
And orbitals, electrons can't exist at a node.
Okay.
Right? And the reason they can't exist at a node is because it's an area of 0 probability, meaning there's no orbital that exists there.
Gotcha. So would that still be considered an aromatic ring?
Mm-hmm.
Would that still be considered aromatic?
These are all part of a benzene ring.
Okay.
Right? The point I want to get out of, the point I'm trying to, or why I'm trying to show you guys this is, where are all these orbitals located? Well, 2 of these combination sets mean what? 2 of these electrons are zipping around the whole ring itself, right? And on the bottom set there, what's happening? 2 electrons are bouncing back and forth between 4 of the atoms. Got it? So what we're going to say in this term that we're going to hear a lot is a delocalized electron cloud. This is where that comes from. These electrons are hopping around all the different atoms. Okay? If I just look at this, okay, if I'm just, well, you guys trying to get that other thing off the screen. Big benzene, all right. If I'm just looking at this, right, it looks like we have discrete pi bonds that are just existing between those 2 carbon atoms. Right? Do you guys get what I mean with that? But I asked you guys, could you draw resonance structures? Yeah, sure. But we would still have 3 discrete pi bonds. But that's not the case. These electrons are delocalized around the whole ring. Got it? But we don't want to draw these stupid orbitals every time we do this. So this is a perfect approximation for that. We understand what this means. We understand that because this is a flat planar system that has a Huckle number of electrons, that has usable p orbitals next to each other. Okay, we set up a system where these electrons are in a delocalized orbital set. Got it? Yes, following along with us. Yes.
So those 3 pi bonds represent the hamburger bun
Mm-hmm.
on top and on the bottom.
You can think of it. One represents the other, right? So in reality, what we'll often see, and you'll see me doing it when I forget, right? You'll see this being drawn in, right? Does this make more sense now? Right? This is just saying, hey, now we've got a delocalized Huckle number of electrons around this system. So in reality, this is kind of a de facto way of defining a aromatic system. Okay? The reason why we can say that these are delocalized is because of those images we had there previously. Got it? So, who cares, right? Oh, great, right? Aromaticity imparts a level of stability, and you could even say a level of unreactiveness to an aromatic system. Okay? And what I mean is, Kind of what I told you guys for OChem 1. What did I say about aromatic systems in OChem 1? Leave them alone, right? We're not going to do anything with them yet. Leave them over there. They're not reactive for what we're doing. And that's mostly true, okay? Sort of. It's mostly true until it's not, right? So if I try to hydrogenate this under the conditions which we've, let's say, come to expect, right? Nothing happens. Okay? No reaction. Because of the aromaticity and the stability imparted from being able to make these conjugated pi systems, these hamburger buns, right? It makes the activation energy for certain reactions high, right? Higher than what we are normally able to access. Now, if you sit here and you crank this up to like 1,000 psi under, I think it's like 850 Celsius, yeah, sure, okay, we can break that ring, okay? Well, we have to add significantly more energy to be able to do that. Which is good, right? Because what does that mean? That means we have a certain level of selectivity of the reactions that affect a benzene ring or an aromatic ring. You guys catch what I mean with that? We can hydrogenate the crap out of the rest of our molecule, and benzene ring is going to stay there, right? That's good. We don't have to put a protecting group and any of this other kind of annoying stuff, right? It's just not going to react. Okay? Right? However, even if we meet only part of this, right? Even if we only meet part of the requirements, okay, we have a ring, we've got some pi bonds, but it's on a Huckle number, right? So that's not an aromatic system. Will this react? Yes, right? Dr. H, that's a conjugated set of pi bonds. You told us that that stabilizes. Yeah, it does stabilize it. But it's not aromatic, right? So our conjugated alkenes will still react under the conditions that we've learned so far. Got it? Do you guys know how to hydrate an alkene? Sure. You guys know how to hydrogenate it? Sure. Can you guys do a halogenation? Sure. Right? All that stuff works with conjugated systems. The caveat being we have to pay attention to the kinetic versus the thermodynamic products. Right? But there's no special setup, I guess, needed for a conjugated system. But for aromatics, we're going to have to change how we approach the reactivity of it. AKA, guess what we get to learn? New mechanisms, right? We have to completely change the way we react things. Don't worry. It'll still be complicated, right? Nothing can be easy. But we're limited, okay? Because we're dealing with an aromatic system. So it's going to be a lot of resonance structures, that's all. Okay? Good? All right. What are these nuggets of wisdom? All right. I like how I bring my notes and I don't use them anyway. I'm like, oh, okay, I should talk about that next week. So, can you guys draw resonance structures of this molecule? One of you guys. All right. Now you'll notice a 5-pound bag of John.
Yes.
That I will sit here and eat while you guys have to do all the work. Let's see. What's first on top here? What? Look at this. Here's the whole top is all blue raspberry. You'll know it's the best flavor. We'll put that there. All right. How many resonance structures can we draw from this?
Three.
Oh, Jesus. What else am I going to do? Oh, do a dance. What do you want? Any? Grape sucks. I'll do that. Just because I care. Thanks for taking one for the team. 3 resonance structures, right? You guys get them all? Yes. This is important. Okay. Try and be serious for the next like 20 seconds. It burns, right? Right? But it's extremely important to be able to draw the resonance structures. You have to do it. Right? That's the only way we're going to get through the rest of this semester. Pretty much every mechanism that we get through from now on, it's going to involve some kind of resonance structure where we push electron density around to a different atom, and then it's going to react, right? That kind of thing. Got it? You have to be able to do it. All right, we're on display again. No, okay, they left. No free learning. All right. So with the criteria that we have to assess aromaticity, right? We know this isn't a ring. Yeah, I got that, right? You guys got it? What's up?
What happens, can't you like make it a ring in a sense?
So if we make a completely different molecule? So hang on to that thought though, but we'll get back to that later, right? It's an interesting observation. I think I know what you're getting at with it, so but hang on to that, okay? So we know this isn't a ring, of course, but can these p orbitals talk to each other? Are these all usable p orbitals? Well, remember, the p orbitals that make the pi bonds, right? Those are considered usable. And what else did I say? Vacant p orbitals are also usable. Got it? What's the hybridization of that carbocation? It's sp2. What's the geometry of sp2? It's planar. What's the geometry of all the double bonds? Planar. So these are all in a plane with each other also. Got it? Remember, one of the rules that we had to have behind the scenes there for aromaticity is that this has to be a completely planar molecule, right? So the same rules apply here, okay? The same rules apply here. Those still have to be planar to be able to draw those resonance structures. Now this is something we never talked about before, right? So does it change anything that you guys are doing? No, right? It's all still the same. But now we have to start, really paying attention to that geometry here, okay? You guys following along with this? If you guys could follow along with that and assess all that, then this is where I'm trying to lead into how we go to aromaticity, right? Good? All right. So can we draw resonance structures here? How many resonance structures can we draw?
Draw 2.
Do you guys think, did I really change anything from what I just drew up there before?
No, you can try.
So how many resonance structures can I do? Three, got it? No children. But you guys needed some pep today, right? Had to wake up. Fire alarm, Dr. Is that a ring? Are all the atoms able to talk with each other? Do they all have usable p orbitals on them? Oh, you guys got a 50-50 shot here, right? Can all the atoms in this ring talk to each other through the p orbitals? No, right? What's this guy right here? It's a carbon. Alright, what flavor do you want? No, you don't want one?
Oh, surprising.
Apple sucks too. Oh, sorry, I throw it at your feet here, my bad. Good social distancing, right? And,
Yeah.
I throw the virus to you.
I thought you were gonna hit me in the middle of the forehead.
Wait a minute, yeah, no, I like this idea better. Here, throw it back. I was right. Right? That's an sp3 hybridized carbon. Are there any open orbitals on an sp3 hybridized carbon? AKA, are there any unhybridized p orbitals? No, right? AKA, can we draw a resonance structure in any way to that carbon with a dot on it? No. You guys catch what I mean with this? So all these atoms can't talk to each other.
Would it still be a conjugated system?
The two, yeah, right? All the five other carbons in there can all talk to each other, right? So that would be conjugated. But because that one carbon kind of disrupts the telephone game, right? You guys know what I mean? Right? If I tell something over here and say, all right, everyone, pass the message down. By the time it gets to camera, it's completely wrong, right? Use concentrated sulfuric acid. 6 molar, okay. But you guys get what I mean, though? Along the way, there's some kind of communication that can't happen, right? Because there is no available p orbital on that ring. Got it? Then this can't be aromatic. Okay?
Would that be the same with the strand one up there?
Well, it's not a ring, right?
Well, I mean, all things considered, like.
Yeah, in both cases, you're still conjugated, yes. But not aromatic. All right, so let's get rid of that carbon that's causing us problems, right? Okay. Struggling with the 5 over ring. Just wait till we get to 7. Oh no. Look, I'm just saying, I told you what the title of the class is, right? It's very clearly written online. So all we're going to end up doing from now on is a bunch of hexagons. So. Well, I was trying to encourage her that you shouldn't have to worry too much about the 5 card rings. That's what I was saying. Thank you, Annie. a thing, so we must assess a thing, right? Is it a ring? Can all the carbon atoms talk to each other? AKA, can we draw a bunch of resonance structures? Does every atom have an available p orbital? Uh-huh. So it's a ring, it's planar, they can all talk to each other, so we have an aromatic compound, right? See, that's not. What did you have last time?
Apple, please no more apple Electrons.
Blue raspberry?
Yes.
I had the four. Alright, I'm getting better. Did you guys forget to check your Huckle number before you said yes? How many electrons are part of this telephone game? How many electrons are part of this telephone game? You can go and answer. Oh, I thought you looked like you were waiting to, I'm sorry, I misinterpreted. One? Who said one? You guys owe me geometry. I got it, Dr. H. The answer's one. It's four, right? How many pi bonds are there? Two. How many electrons are available at that carbocation? Give you a hint, it's got a positive charge. None, right? There's no electrons at that positive charge. What's the red one? Generic red one. Cherry? That was the first red one. Those are my favorites, so you're welcome. Right. Okay? You guys see it? There's 4 electrons available, 2 in each of the pi bonds. How many electrons are available at a carbocation? None. 0. Il zilcho. Right? Does that make sense?
What about the electrons in the single bonds?
Those are in the single bonds. They're in the sp2 hybridized. Right? How many sp2 hybridized orbitals are there? S plus 2p makes 4, 3 orbitals. How many electrons are at that carbon? 6, right? 2 living in each of those sp2s. So we don't have any available at the top, right? Got it? So is this an aromatic system? No, right? It does not meet the Huckle requirement. Okay, let's give it some more electrons then, right? All right. Now we've given it some, we've gotten rid of our positive charge to the magic of erasing it. Okay? So now we've got a ring, right? Can everything talk to each other?
No.
No, crap. Okay. Let's try again. Now let's say I put a negative charge on that carbon. Okay. Sure.
That was too much.
Okay, now I put a negative charge there. So ignoring the whole argument about a, well, I don't know if I should say ignoring. Can you guys push that negative charge around the ring using resonance? Yes. Can you guys walk all the electrons around each other, the ring, continuously? AKA, could you completely delocalize the electrons there? Yes. You should be able to, is the other end of that, right? So this is a ring, right? We have usable p orbitals. How many electrons are present? 6. Is 6 a Huckle number? Yes. So is this an aromatic ring? Yes, it is. Okay. So what's the point I'm trying to make here also? Right? Well, there's a couple, right? We talked about carbocations, now we talk about carbanions. Or we could even expand this to the argument of lone pairs, right? Because remember, a negative charge on a carbon just means that there's a lone pair on that carbon. That lone pair sits in a usable p orbital. Now, it just so happens to be that that's not a unhybridized p orbital. But what did I say? Well, if something can form an aromatic ring, those will make themselves usable to delocalize this stuff, okay? And so that's why I'm always very hesitant to say, oh, it's unhybridized p orbitals. Well, this is the second most common aromatic ring that you guys will run into, at least in this class probably, right? And there's already a counterexample of it, okay? So lone pairs can work, open orbital sets can work, double bonds can work, okay? Good? All right. So we venture into the bizarre, maybe. Okay. Is it a ring?
Yes.
Uh-huh. Does every atom in the ring have a usable p orbital? Can all those p orbitals talk with each other? Therefore, this is an aromatic system. No.
Doesn't meet the Huckle number.
How wrong you are. Notice n can go from 0 to infinity, right? So if n equals 0, our Huckle number is 2, okay? So this is the smallest aromatic system that can be made, okay? So how often will we see it? Only when I wanted to get you guys in class, right? Boom, got it. Boy, do they feel worse about themselves now, and I'm done for the day. Right? I mean, it's such a quirky example, right? But this is literally the only, as far as I know, this is literally the only way that you can practically make an aromatic system, right? That has n equals 0. I'm sure nobody watches these videos anyway, so, but just for argument's sake, but somebody's going to watch these and say, no, Dr. H, you understand, if you make a 4-membered ring and put 2 positive charges, blah, 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 right? Okay, you got it, whatever, right? So, for all practical purposes, this is the smallest aromatic and the only one that I know of where n equals 0, okay? But it is possible, and actually this is surprisingly stable, right? Despite how it might seem, like you got a positive charge and a 3-membered ring with a pi bond in there, right? Why is that so unusual? What's the geometry of any pi bond? Trigonoplanar, and what do the bond angles want to be?
One
120, right? Do you want more? Okay, all right. yeah. You're welcome to it. I just see how weird the choice to you, right? So, but what's the angles inside this ring here? 60, right? Gross. We're forcing 120 all the way down to 60. There's a whole lot of ring strain in there, right? But despite all that, this is actually surprisingly stable, right? Because we have this magic that happens with the aromatic systems. Got it? Cool. So you can only set the number of example. What do we have here? Does your tablet like make a 7-membered for you? That'd be pretty cool if it did, honestly. No. I was just gonna. I thought you were proud of your 7-membered ring. That was gonna work.
It does.
No.
It looks like this.
Are you kidding me?
You just
It's like you were looking at a Picasso, like mine's better. It's just like Guernica. Come on. It does actually make a 7?
does. It's not.
How does it look? Or did you already erase it? Oh, okay, no. I know, it's super cool. Anyway, right, so what do we have? Do we have a ring? Yeah. Can all the carbons in the ring talk to each other? Yeah. Right? Does it have a Huckle number? Yes. So is this an aromatic system? Yes. Right? So this is another example of where N equals 6 for an aromatic system, right? So we talked about benzene. Oh, I forgot to give you guys a name for some of these things. I'm sorry. This one right here is pretty common. So we Cyclopenta, Diene, Anion, right? Which is, no one cares about that. We typically just abbreviate that as CP, right? We'll see this again actually in lab, if we make it that far in lab. We actually do have those chemicals in, so probably, where we'll actually use something called ferrocene, and we'll do one of these reactions we're going to learn. It makes pretty red and yellow and blue colors, so it's a really cool lab. But this is a very common thing. Despite this being an anion, this stuff is pretty stable to moisture and air. You might expect a carbon with a negative charge to be extremely reactive, right? If we take a look at some of those other carbons with negative charges that we run into, like the Grignards and the magnesium and the organolithiums, the instant they touch moisture, right? But this stuff right here, right, you guys can lay it out on the bench top and everything. Right? No, it's all right. It's not going to do anything, right? It's stable because it forms an aromatic system, and so that negative charge is completely delocalized. Breaking an aromatic system is a very, very energetically unfavorable step. AKA, if I were to make that negative charge on that CP react with something else, it would break the entire aromaticity, right? And so that wouldn't be something good. So sometimes you'll see CP just abbreviated, very similar to what you see for benzene, right? You'll just see that right there, right? So if you ever see that symbol, we got that delocalized circle and just a negative charge on the inside there. Right? And similarly, for this one, which we'll never see again, I think the book does it like that, right? So a little triangle with a circle and a plus in there. Yeah, that's just one of those examples that we have again. Yeah, we won't really do anything with that. That's all those noises. It's like the tornado. Yeah. No, I was up near. Actually, Orlando is one of the most busiest areas. That region, because we got the prevailing winds like up the Atlantic and then down from the Gulf, and it just kind of meets in the middle there. So I almost saw one point. I was going to a demolition derby, which, oh my gosh, those things are so fun, right? But it was in Sanford out there, like we were going in a tornado, like down. So, which if you guys have never seen like a water spout or something, it is absolutely like breathtaking to see that. It's scary as crap, right? You know, but if you ever see, I mean, it's just like, talk about just like raw nature, right? You know, it's like, it is absolutely amazing. But as long as it's out at sea, then nobody gets hurt when it's happy. What's up?
Have you seen one on the beach?
Oh yeah. No, when I grew up on the coast of North Carolina, like they were.
Those are so nice to see.
Yeah, no, it's I mean, it's awe-inspiring. It really is. Right? We think we're in control of the planet, but we're often at its mercy in many ways. Anyway, different argument for different day. So we have this thing here. Now this is something you guys have seen before, plenty of times. All right? All right. This is our good old buddy and helpful Pyridine. Right? This is our buddy Pyridine. Is this a ring?
Yes.
Yes. Does every atom have a usable p orbital? Yes. How many electrons are present? 6. So is this an aromatic system? Absolutely. Now, for you keen-eyed observers out there, what do you notice? Well, we don't have a carbon in here, right? We've got what we would call a heteroatom, a non-carbon atom. So this is a heterocyclic, right, aromatic system. So if you ever see that kind of fancy-sounding term, it just means, hey, we got something that's not a carbon in there, right? Yeah?
Are we not counting the lone pair on the nitrogen?
Aha.
Is it
Aha. Right? For the, you want to talk about? Oh, well, we don't go to, yeah, whatever. I'll let you pick one out. So, is this, to answer, I think you asked, is this planar? If it meets all those requirements, we can just assume it is, right? Did you ask? I forget.
Yeah, like, is it sp2 or what?
Yeah, it is, right? It's doubly bound there, right? So it's still sp2, and if it checks all the other boxes for aromatic, we can assume that it's going to be planar, right? Okay. Just one, right? Okay, I gotta keep an eye. Look, I've only got 5 pounds, okay? Right? But here's the thing. So the question was asked, hey, wait a minute. What about this lone pair that's sticking out here? Brilliant observation. Okay? I believe it's in the textbook that answers this exact question. Let me see if I can find it real quick. I thought I had it open, but not. If not, I'll give you guys my drawing of it, and it'll look fantastic. Yes, so page 766. Okay, so page 766. So I'll give you guys my best interpretation of it. Okay, so imagine for a minute that we're going to look at this benzene, the pyridine ring, from the side. Okay, so we're not looking at it. We're kind of tilting ourselves like this and looking at it from the side. Okay, and so what I mean, or the best way I can kind of draw it. So there's our nitrogen, right? And we have kind of the carbons in the back, and then the carbons out front here, right? You guys kind of see what I'm saying? Basically, kind of tilting it. Doesn't that look like garbage? Yeah. You made fun of my drawing. Okay? So if you imagine, right, we're kind of looking at it. This is a planar system, right? You guys get what I mean with this? Okay? We have our hamburger bun that's above and below here, right? That's our hamburger bun that is our aromatic system. Where is that lone pair then? That lone pair is sticking out here, okay? It's 90 degrees from that hamburger bun set of orbitals. Orthogonal, right? It's orthogonal to the electron, or to the pi cloud. AKA what? The definition of an aromatic system means that all of the p orbitals have to be in the same plane. Otherwise, they can't talk to each other. Is that orthogonal lone pair in the same plane as the other ones? No, it is not. Therefore, it is not involved in the aromatic system. That means it's still reactive, and that nitrogen on that pyridine ring is very reactive. Okay? You guys with me on that?
What if the lone pair is like a hydrogen bond? Like, is aromatic or?
If it's orthogonal there, yeah, right? Okay, what's up?
So if it's orthogonal,
Yep,
there's still an aromatic ring,
yep.
and that part doesn't react with but like the bond out.
That reacts differently, I would say. It will still react, it can still react. It's a separate entity from that lone pair that's there, right? That's all it is.
Okay.
Good? Cool. So I think that's it for today. We'll pick this back up on Monday there, and we'll keep going through.